I would like to tell you about recent research done with Hassanave and the system that we built called PhotoProof for authenticating images. And let's start with some motivation. Photographic images are nowadays ubiquitous, especially in the digital medium, and they are used as evidence that a certain physical scene once happened in reality. This happens in numerous contexts, in the legal context as legal evidence, in journalism, in politics, in social interactions of all sorts, whether positive or negative, as in shaming or extortion. It happens in dating websites as proofs of physical attractiveness. And perhaps in the most important form of images on the internet that frequently stretch our credulity about physics and physique, cats. And in all of these cases, there's the question of, is the claim true? Is the evidence really truthful? And of course, with the ease of digital manipulation, it's often false. Taking dating website, for example, well, there's an app for that. Facetune would fix up minor blemishes. And clearly, the presence of a bunch of pixels in a properly formatted file construes very weak evidence that something ever happened in reality. And it's something that even major news venues fall prey to, and there have been many fiascos about fake images making it to top newspapers and journals, and it's a concern for everyone from Reuters to DARPA nowadays. Well, clearly what we need then is an image authentication scheme that allows someone to capture an image and transmit that image to a viewer. And along with that image, we would like to also have some kind of proving and verification mechanism that would allow us to send a proof, and the proof would be verified. Well, sounds very straightforward, and there's the naive solution of simply signing every image on the camera. It's something that Nikon and Canon have already implemented on some of their camera. In their case, preposterously bad, but it could be done properly. But even if we implemented this properly and we kept the key secure and we didn't use the same secret key on every camera like they did, there's still a functionality issue. Because any change to an image will invalidate the corresponding digital signature by design, by definition of digital signatures. But in practice, maybe the image was originally captured by a 24-megapixel camera and is somewhat underexposed, and there's junk around it that needs to be cropped out and rotated and so forth. And none of this would detract from the authenticity of the image. So we would like to have some degrees of freedom, but clearly not others. So we want to be able to specify some set of legitimate or permissible transformations that comply with whatever is our view of authenticity in a particular application. Moreover, we would like to allow repeated editing. After cropping, maybe some brightness adjustment, some rotation. All of these will preserve the authenticity of the image. And we want to preserve soundness in the sense that images will pass verification if and only if they resulted from a series of permissible transformations. For efficiency, we want succinctness, meaning that proofs are small and can be quickly verified. And often we also want the proofs to be zero knowledge in the sense that they do not reveal anything about the final image other than its authenticity in the affirmation sense. So as a quick use case, let's go back to dating website. Photos should reflect what users really look like, which they dictates a set of transformations that we can haggle over. We also want to make sure that if a transformation loses information, like cropping, then that information is really lost. For example, this attractive picture right here may originate in a somewhat less attractive picture, and we want the user to be able to crop just the relevant portion while hiding the rest. So I think this is a very, very reasonable set of properties to wish for. And indeed, the desire for this has been recognized for decades now. We can look at schemes in the literature beyond the trivial digital signature scheme. There is a series of works coming mainly from the computer graphics community that uses the robust hash technique. And what they say basically is, let's not sign the full original image, but distill it into something and then sign the something. And the something would be invariant to the transformations that we desire. So for example, if we want an image to be rotatable, the rotations are in the class of permissible transformations, then, well, on the camera, we would compute the radon transform of the image, which is invariant to rotations. We sign that, and everyone who wants to verify would compute the same transform and compare that to the signature. If we want to allow a bit of noise or JPEG artifacts, let's just downscale the image and downscale the image and so forth. The problem with all of these approaches is that they are very specific to the transformations to which that summary is invariant. And each of them allows a few transformations, but no others. Many of them are also inefficient in the sense that that condensed transformed version of the image is large, often proportional to the original image. And many of them also have a very high rate of errors, false negatives and or false positives. So clearly that technique doesn't cut it. It doesn't provide enough generality, performance, or soundness. A work that is closest to us in spirit is in the thesis of Walsh from a few years ago, and it uses trusted hardware, TPM, together with the Nexus OS built on top of that. And the approach there is to have secured platforms perform the transformations and then use TPM attestation to convince us that they did it correctly. The wonderful thing about it is that these platforms can run any computation, and therefore this really supports any class of permissible transformations. But it does rely on trusted hardware. It does have proofs whose size grows in the number of edits, and it does not provide zero knowledge. And in this talk, I'll tell you about our system called PhotoProof, which actually achieves all of the goals that we list here, including full flexibility for all images, small, succinct proofs, and zero knowledge. In a nutshell, what the system looks like is the following. There is a setup stage where the system administrator, say the manager of the dating website or the US government attorney general, they decree what is their state of permissible transformations, and they run an algorithm to encode that into a set of public keys used for proving and verifying statement. This is done just once for every application. Then, once the keys are distributed, everyone can capture images. So you can capture an image and then send that along with the signature to a user who might edit that image, for example, flip it, and suppose that flipping is a permissible transformation. Then they can use another algorithm, another software module within the PhotoProof system to create the flipped image, along with the proof that it is authentic. That can later undergo additional transformations, say cropping, resulting in a new image with the corresponding proof and so forth. And any user along this chain can run a verification algorithm on the image and the proof, attesting that it is indeed the result of a sequence of permissible transformations. That is the completeness property. The soundness property is intuitively that if anything else happens, for example, someone tries to airbrush an image, then they will never be able to construct a convincing proof. Any attempt to create a proof and send it to a verifier will result in the verifier recognizing the image as not authentic. So this is what we would like to construct. And our technique for doing this is very different from the old works using image transformations and summaries from the graphics community. Instead, we use cryptographic techniques. We use the paradigm of proof-carrying data, which is a generalization of snarks that Antoine mentioned in the previous talk. And the idea in proof-carrying data, taken abstractly, is that we have some computation, a distributed computation consisting of numerous parties, none of which trusts any other. And they would like to ensure that some property of integrity is preserved throughout the computation. They would like to ensure that the computation is compliant with some policy. And they will produce proofs at every stage of the computation that compliance with the policy is preserved, where every proof attests that all of the computation so far, including retroactively, has preserved the property. The property is defined as a compliance predicate, reasoning about every individual node in the computation. The compliance predicate observes the inputs of the node, the outputs of the node, and some local inputs. In our case, the inputs would be the source image, the output would be the new target image, and the local inputs would be the choice of transformation and its parameters. And then the compliance predicate decides whether this is acceptable or not. PCD gives us the ability to take any such compliance predicate and bake it into a system. So applying that to the problem of image authentication, we think about the lifetime of an image as a distributed computation, in this case, a line graph. We could extend that to more general graphs. Then we express the locally permissible transformations by encoding them into a compliance predicate, and we use a PCD implementation to enforce the compliance of an image throughout the history. So for example, if the set of permissible transformations were cropping, rotations, and flipping, we encode that into a compliance predicate, and then every proof will attest that every step consisted of just one of these three transformations. So we actually implemented this idea. The underlying PCD implementation is that of the libsnark library that we built as part of Skipper Lab. This is an open source implementation. It started as a series of very theoretical works, progressing through increasingly efficient constructions and implementations. An artifact that released as open source 2 years ago, and then additional improvements and open source contributions. And it allows us to write a compliance predicate expressing our application-specific needs. In our case, the compliance predicate reasons about RGB images, and the prototype includes cropping, rotations, flipping, transpose, brightness adjustments, rotations, and so forth, and it can be trivially extended for additional ones. Now, I hope that I convinced you that the mapping between the image authentication problem and that of proof-carrying data is very natural and appealing once recognized. But in practice, realizing this has many challenges. Some of these are mundane engineering concerns of format matching and integration. Others are deep theory questions that arise when you try to do all of the impedance matching, like finding the right theoretical security definitions. In this case, turns out to raise fascinating questions, some of them still open, about having proof-carrying data reason about things that originate in digital signatures for which none of the current parties has the key. The quantifiers end up all wrong and need new treatment. Other are engineering challenges in the realm of implementing the compliance predicate in an efficient way. And the point is that, yes, there are generic compilers that can take high-level representations of computation and transform them into compliance predicates. One of them is the Geppetto system that Antoine mentioned, which can be trivially adapted to this goal. Another such implementation is the TinyRAM GCC compiler of Skipper Lab. The problem with all of this is that they entail a high cost for their generality. And in our case, as you'll see, we are really struggling to reach the realm of practicality, and therefore we found ourselves hard-coding image transformations within the peculiar language of proof-carrying data compliance predicates. And let me exemplify that by looking at rotations. So image rotation by an arbitrary angle theta, you can represent that as multiplication by a rotation matrix consisting of some trigonometric functions of theta. And if you implement that as a compliance predicate, you find yourself expressing that within the language of roughly arithmetic circuits, because that is the native language for the cryptographic scheme. So we need an arithmetic circuit that gets the input image, the output image, the angle, maybe some auxiliary inputs, and decides whether this rotation was done correctly, whether it's permissible. Now, if we were using random access computation, there's a trivial algorithm of doing random lookups with quadratic complexity. But we are stuck with arithmetic circuits, again, because of the underlying representation of the cryptography. A generic reduction would lose us at least an n factor. But in our case, we can do better by using specific algorithms for the problem. A naive implementation using arithmetic circuits would be bad as well, because every pixel could have resulted prior to the transformation from any of n pixels, and therefore the efficiency of a naive implementation would be cubic in the image dimension. But we can use tricks like an alternative representation of the rotation matrix based on composition of shearing matrices, each of which can be implemented using barrel shifters, using n log n gates for every row. And that saves us roughly a factor of n, where n is the image dimension, in the size of the circuit and eventually in the runtime of the prover. Then another trick we can use, just to exemplify, is that of non-deterministic advice. Remember that the local input can include various parameters that the currently executing editing node claim when it went into the transformation. And this allows us to short circuit some computation just by verifying it instead of computing it. For example, given an angle, we still had to compute those nasty trigonometric functions of the angle. And doing that in an arithmetic circuit is very awkward for performance. However, we can just get as extra advice, a non-deterministic witness that the compliance predicate receives in order to get the requisite functions of the angle, and verifying these is much more efficient, just some cubic functions. So there's a whole bunch of tricks like this, and there's a lesson here about the design of such systems, that they really become very domain-specific once you optimize performance for this verification setting. Let's talk about performance. These are some numbers. Let's focus on the last row of images, which are 128 by 128 pixels. There's not very large images, but it's clearly the right size of image because it has roughly the amount of entropy as 1,000 words. In this case, the generator encoding the permissible sets into the public keys runs for about 4 minutes and generates about 4 gigabytes worth of public keys. The prover takes about 5 minutes to prove that a single transformation was indeed legitimate. And this covers all of the transformations concurrently. The size of the proof is just a few kilobytes, and the verifier runs in under a second. And you may know that the numbers are surprisingly similar to those of the previous talk. It's, I think, partly coincidence and partly both teams optimizing their benchmarks to what could run and finish in time for the submission deadline. Now, there are many additional features that PhotoProof has or could easily acquire, including plugins for GIMP or Photoshop, reasoning about metadata and EXIF tags, including edit history, using certificate chains to allow revocation of cameras, and many opens. Can you go back? Thank you. Many problems remain open. The good news is that we've really solved an open, long-standing problem that's been open for 2 decades, at least in the asymptotic sense. In the practical sense, it's on the verge of practicality, and I expect that with additional engineering will soon be useful for larger images. And beside the question of improving performance, There are security questions about attacks at the sensor level. These have been addressed by many prior works. I will not go into these. And there is the tantalizing idea of extending proof-carrying data and reasoning about provenance for additional media types like text, audio, and databases. Thank you very much.
One quick question.
Hey, thanks a lot. So I really like how you're using proof-carrying data to do all this stuff, but at the beginning there's like the analog hole, right? So going back to your dating example, so you prevent someone from airbrushing their photo, but you don't, how do you prevent me, I mean, an unscrupulous person from taking a photograph of a much better looking person, right? And just putting it on their site. Or more to the point, how do you, I mean, it doesn't prevent someone from doing an arbitrary image manipulation and then taking a photo of that manipulated image, right? Because all the signature is doing is signing that the camera took a picture of something, but that something it took a picture of could have been itself totally manipulated.
Yes, this is certainly true, and in this system we only reason about what happens after the sensor. There are certain works that we summarize in this paper, and it's an extended version in Asa's thesis that discuss these challenges. And in a nutshell, there are many things you can do also at that level, like reasoning about the analog signature of the sensor to make sure that it came from an authentic sensor, perhaps in a tamper-proof module, reasoning about focus distances and dynamics of the scene that will capture many inexpensive forms of treachery.
But putting someone else's picture on my dating site
is left as an open problem.
There you go.
All right, that's all we have time for. Thank you, Aaron.